In this PowerPoint, we'll discuss two applications of the ideal gas law. In particular, we'll discuss how to use it to calculate gaseous density and molar mass. Let's start with using the ideal gas law to calculate density. The density of a gas is related to its molar mass. And determining density is one way of determining the molar mass of an unknown gas and potentially identifying it. I'm going to show you the derivation for the density form of the ideal gas law here, but ultimately you'll just need to be able to use the final formula to solve for either density or molar mass. So remember that density is mass divided by volume. We often represent density in chemistry using the Greek symbol rho. For gases, the units we use for mass and volume are actually grams over liters because gases occupy so much space. Now, if we look at the ideal gas law, PV equals nRT, we can find liters as the unit of volume. There's actually no unit for mass in the ideal gas law, but we do have something we can relate to mass, and that's moles. We know that molar mass, which I'm going to abbreviate MM, is equal to the grams of a substance over 1 mole, or the grams per moles. So we can rearrange this to actually solve for moles, the variable we have in the ideal gas law, as grams divided by molar mass. And we can now substitute this expression into our ideal gas law, and we incorporate a unit for grams. So this is what that looks like. Pressure times volume equals grams divided by molar mass of the gas times R, the ideal gas constant, times T, temperature. Now what I want to do in order to derive the density formula of the ideal gas law is actually get grams divided by volume on one side by itself, because grams divided by volume, or liters, is the density of a gas. So to do this, I'm going to first get molar mass out of my denominator by multiplying both sides by molar mass. It cancels out on the right, and I end up with pressure times volume times molar mass equals the grams, or the mass of the substance, times R times T. Now, in order to get grams divided by volume, I can just divide both sides by V. It'll cancel out on the left-hand side, and I'll be left with pressure times molar mass equals grams divided by volume times RT. I can then get my grams divided by volume, my density term, all by itself by dividing both sides by R and T. And I end up with pressure times molar mass divided by R divided by T equals grams over volume. And since I know that volume is in units of liters and grams per liter is the unit of gaseous density, I can actually substitute rho, the Greek symbol for density, into the formula, and I get density of a gas equals pressure times molar mass divided by R divided by T. Here's the final density variation of the ideal gas law again, where density is represented by the Greek letter rho, and MM in script stands for molar mass in units of grams per mole. Another rearrangement of this formula solves for molar mass directly instead of density. This is known as the molar mass variation, and in this rearrangement, M stands for mass in units of grams, and V, of course, is volume in units of liters. So we can use either formula to solve for what we need. Let's look at a couple of examples. Let's calculate the density of nitrogen gas at 125 degrees Celsius and a pressure of 755 millimeters of mercury. So we're given temperature and pressure, and we're asked to find the density. And since this is gaseous nitrogen, we can use the density variation of the ideal gas law. Now, temperature in the ideal gas law is always in units of Kelvin. So we do need to add 273.15 to our Celsius temperature to convert that into Kelvin, 398.15 Kelvin. And pressure is always in units of atmospheres for the ideal gas law. So we need to convert by using the conversion factor for atmospheres to millimeters of mercury. 1 atmosphere equals 760 millimeters of mercury. We divide by 760 so that the millimeters of mercury cancel out, and we get 0.9934 atm. I'm carrying more significant figures than I need until the very end. Now all we need for the calculation is the molar mass. For nitrogen, nitrogen is a diatomic element. That means when it's found in its elemental form, it's always N2. So that's a molar mass of 28.02 grams per mole. And R, the ideal gas constant, 0.08206 liters times atmospheres divided by moles divided by Kelvin. So we substitute these values into our ideal gas law. And notice what happens to the units. Atmospheres cancels out. And moles will cancel out, as will Kelvin. The only units that we're left with are grams over liters. And that, of course, is the unit that we need for density, 0.852 grams per liter. And I've simply rounded to 3 significant figures at the end to match the number of significant figures in my original measurements. So let's look at a molar mass application next. A sample of gas has a mass of 0.31 grams. Its volume is 0.225 liters at a temperature of 55 degrees Celsius and a pressure of 886 millimeters of mercury. Find its molar mass. So we're given mass, volume, temperature, and pressure. We're asked to find molar mass, which means that we should use the molar mass variation of the ideal gas law. We still need to make sure that all our units are in the correct form for the ideal gas law. So mass is in units of grams, which is appropriate. Volume is in liters. Temperature does need to be in Kelvin, so we add 273.15 to our degrees Celsius. And our pressure needs to be in units of atmospheres. So we know that 1 atmosphere equals 760 millimeters of mercury. So we set up our conversion factor to divide by 760 millimeters of mercury. So our units cancel out, and we're left with 1.1658 atmospheres. We will still need the ideal gas constant, R, 0.08206 liters times atmospheres divided by moles divided by Kelvin. So this number usually is not given to you in a problem, and it's just expected that you will know what the value is. We substitute these numbers into our formula, and notice what happens to our units. Kelvin cancels out. Atmospheres cancel out. Liters cancel out. We're left with our final units of grams per mole. And I rounded 2 significant figures here to match the least number of significant figures in my measurements, which is the mass number, which has 2 significant figures. So my molar mass is 32 grams per mole. And this can give me a clue as to a potential identity for this gas. One gas that has this particular molar mass is oxygen, O2. So in summary, these are the 2 variations on the ideal gas law that are the most commonly used. They are the density variation and the molar mass variation.